Hello everyone, welcome back to Dragonfly Engineering. So this week we got a special episode because we're getting back on the Stoker Steam Engine project with Keith Rucker and his YouTube channel, Vintage Machinery, and also his website, vintagemachinery.org. So Keith and I have worked together on several parts of the Stoker Steam Engine in the past, one of which is a piston rod from several years ago. And recently, or this spring, it was a wrist pin that connects the piston rod to the linear slide. Well, the next project, which he said he needs some CNC assistance with, will be these valve sleeves. Now, these are cast iron tubes with like a lathed profile in the middle. We can take a look at the CAD or the computer CAD so you can get a better view. But there's two landings in here where the equivalent of like a hydraulic spindle actually moves back and forth and ports the steam into the two cylinders of the steam engine. And in this case, with steam engines, unlike internal combustion engines, every stroke has steam power. So all of the ports on this cylinder basically port the steam, to the different actions of this Stoker steam engine. Keith had to press these old sleeves out of the engine block of the Stoker steam engine. And when that happened, the press force was so high that these cast iron sleeves basically broke apart. So he super glued them back together so that I could recreate them in CAD. And then we are going to have two operations. One is to lathe cut the inside profile, basically the two valve seats inside of this tube. The second operation is going to be to CNC all of these ports using the 5-axis Haas milling machine over there. That'll probably be a separate episode for the 5-axis CNC operation on the outside. This episode we are going to tackle turning the inside valve seats of this tube. And to do that, I had to make quite a beefy boring bar, a custom boring bar for the CNC lathe over there. I did see when Keith Rucker was turning these cast iron blanks, Keith had an episode recently where he turned these down. And I did see that his boring bar looked like it was flexing a little bit.
I can see some flex in the boring bar, but as long as it's sticking out, I'm not surprised. Let's see if we can get a good cut through here. And just once I get a uniform cut going on, it won't be as big of a deal. It'll be flexing, but it'll be pretty much a constant flex throughout, so you'll end up with a good bore.
And that concerned me because, Keith's got big manual lathes. My CNC lathe is a little bit smaller. So I decided to make a custom boring bar that is substantial so that we get the precision valve seats with a good finish inside of this cast iron tube. To make that boring bar, which is probably a different episode as well, which probably already came out, I'm using the test piece for the Stoker steam engine piston rod that was used. So that's 1.5 inch diameter by about 20 inches long. Shaft steel, so 4130 steel, and it's pretty hard and tough stuff. So yeah, the first step was to make that boring bar to get a nice precision surface on the inside of these. Oh, and by the way, the Stoker steam engine is called that because it stokes the coal from the coal tender in the Nashville Steam Locomotive 576, which is in Tennessee. This is a big locomotive that's being restored, and the Stoker steam engine is an accessory that sits in the coal tender, and it runs a auger that basically feeds coal into the main steam engine or steam locomotive itself. Anyway, so that's what the Stoker steam engine does. But anyway, yeah, it's a dual piston cast iron steam engine, which is about the size of this desk.
On this particular engine, we basically have some sleeves, some cylinder sleeves that fit up in here. You've got a basically it's almost like a piston that goes back and forth in there that ports the steam into the right direction going into these engines. When I got this engine, the sleeves that were in here were very pitted beyond really being able to use, and we actually were able to press those sleeves out. They are where you can replace them. I was able to get them out with a hydraulic press.
How about if we go over to the CNC lathe and I will chuck up this preform that Keith sent me, and we will turn the inside profile, the valve seats of our Stoker Steam engine valve sleeve. All right, I'll meet you over at the lathe. All right, we're over at the Track TRL 1630 SX CNC lathe. This is from the Southwest Industries, of the Proto-Track series, and it's pretty helpful. You can use it as a manual lathe or a CNC lathe, or in our case, some sort of combination of the two. But we are going to follow a program that is in the controller that shows the profile of the inside of this cylinder. And this boring bar is going to basically go all the way through this cylinder and turn the entire face on the inside. So to do that, we do need to stand the cylinder off from the face of our 3-jaw chuck. And unfortunately, I do have just a 3-jaw chuck here, so I may have to shim 1 or 2 of the jaws so that we can get a good concentricity of this tube that Keith turned on in his shop to be repeatable in concentricity on this lathe. And then we've got a steady rest here that will hold the backside, and Keith also did the same thing on his Monarch lathe, I believe. But the difference is that we've got the Mondo homemade super boring bar here that will turn the inside. With like a new lathe tip right here, for steel, and it's a 14 thousandths tip diameter. We could talk a little bit about tip diameters and bar flexure and surface finish a little later. All right, so I am going to load our stock into the 3-jaw chuck here. And the wheels, I actually ran one of these cylinders already. So my steady rest actually can help me line up my stock pretty good here. And I do have a couple of 1/2-inch parallels because we need to have our part actually extend beyond the face of the chuck because this lathe tool isn't the leading edge. So there's some extra bar stock on the end of the cutting tip of our lathe tool here. I'll zoom in on that. But yeah, let's set the parallels and we will knock our cylinder into concentricity with the chuck. I'll probably move the camera around for that. Now I do have these spacers that interleave on the chuck jaws with magnets in the back, which are handy to use, except that again, our boring bar would wind up banging into this thing. So I need to have our cylinder pretty much just suspended and clearance for the tip of the boring bar to travel so that the lathe bit can actually cut to the end of the tube. So loosen that up a little bit, and I'm just going to lay this first parallel across the bottom 2 chucks, and then the top one pretty much just going to push square against the lathe chuck itself so that we get 4 points of contact on our cylinder. And I'm kind of putting some snug force on the cylinder as I tighten, and then you'll see that the parallel will fall away as we tighten up. I don't think I really need to bump this thing in. It's just we want, well, we're going to actually square up the stock on the chuck anyway. This is mostly just to get a clearance gap in the back here. So I'm going to tighten this up. This chuck is pretty accurate, even though it's a 3-jaw. So we will get the dial indicator and see how we are on concentricity. Hopefully I don't have to do any shimming, but I almost certainly have to shim one of these jaws. So I'm going to magnet this Nova flex arm onto the way of the lathe, loosen it up. And you got to get your arm in there so that it won't get bumped by the lathe jaws either. So we'll test travel, and I'm going to bump it there. All right, that clears. Yeah, and it looks like, I guess I should back off our rollers on the steady rest so I don't get any influence from the roller on getting this end of the cylinder to be lined up and centered on the lathe chuck. If I had a 4-jaw, then I could just push and pull the jaws around, but I don't have one ready to load on this lathe. I don't know if you can see, you probably can't see that dial. But as I turn, I'm seeing about 3 thousandths walk off. So if we go out to the end, now that could just be that the cylinder is not dialed in correctly. We're getting the same 3 thousandths out here. So maybe I'll bump around with the rubber mallet and figure out if we're shifted or if we're just got an angle problem. This is about 4 thousandths out. So if I give it a little tap, I like to pull on the stock and then tap it to reduce the recoil. So that's about 2.5 thousandths. Looks like there was an offset too. That made it worse. All right, I'm going to tighten this chuck up some more. Sometimes just tightening your chuck helps. See, there we're within 1 thousandths total run out. So that's not bad. But how are we doing over here? Are we actually offset in the jaws, or were we just crooked the whole time? So I'm going to move our indicator over. I don't know. I mean, it's within 1 thousandths, maybe 1.5 thousandths. So I may be okay. There's a little spot that I keep hitting. Some of this may be an indentation in the cast. I think I see it actually. Let me move over. Yeah, the needle is like going multiple directions instead of one true sinusoidal. So we are within 1,000. So actually this chuck, without any shims, was able to get this cylinder centered within 1,000ths, which is nice to see. I'm going to move back over. I'm trying to put constant force on the spindle to avoid any backlash from the bearings. Yeah, we're within 1,000ths. So that's kind of incredible. This is a good chuck, but I didn't think it'd be that good, where I just do a little bumping and then we're centered all the way throughout. All right, well, let's move on to the next steps. I'm going to tighten this stock down a little better and keep checking our concentricity. And we've got our gap for clearing our boring bar set. So there we go. Within 1,000ths total run out. So that's plus or minus half 1,000ths. All right, I may do one more check all the way at the end of the stock, which you may not be able to see on the camera. Basically where the center or the steady rest is going to support the stock. And that looks good too. All right, we are set. All right, so we can bring our steady rest down. Let me back this bearing off. I'll clean off the parting line. And then we clamp it with this flip down locking nut. It's just hand tight. Now what we want to do is start to bring in our bearings very slightly snug, because we don't want to push our stock off of our trued in position that we just found with the indicator. And I'm just the slightest force to drive these roller bearings onto the stock. There's like a screw drive in here, probably an Acme thread. And I'm listening and seeing to see that our bearings are going to start spinning. So that one started spinning. The top one started spinning. And the back one is spinning. You can also feel it. And you'll start to hear a little ring from the bearings, and the better lined up you are, the less noise you're going to hear. But you can get chips and things that get into the ways, or you create a way on your cylinder, and your bearings basically have zero tolerance. So if you get chips and stuff, then you'll start hearing chips getting smushed, and you don't want it to be too much of a thing, because it could also push your cylinder out of square. And then we'll tighten down our 3 engagements with the bearings, so they don't push back as chips and stuff start to contaminate and cause problems, which we always want to minimize. But I don't have a whole lot of travel on this carriage, which basically references, or this steady rest references this second rail back here, this triangular rail, and then the flat here, which is similar to how the main carriage references this. The main carriage references this primary triangular rail in the front and then a flat in the back. Well, your accessories for your lathe can pick up on the second set of rail and flat, and that's what we got. So you tighten it down, and it locks square against this triangular rail, and then you tighten up your bearings to hold your stock in place. So now we can test out our setup I'm going to turn the spindle on. And that sounds about right. Could add oil. And yeah, there we go. We'll listen for a while to let it settle in. We're creating a race right there on the stock. That's sounding pretty good. It'll find its worn kind of bearing surface, and the wheels will get a little less loud, but they're always going to be a little noisy. There's also brass rub tips that you can get, but I like the wheel bearings better. All right, I think we are getting close to turning our part. So you can probably see the lathe tip on our boring bar, this guy right here. So I'm just loosening the screw in the custom boring bar, which, like I mentioned, will probably be a separate episode where we made the beast here. One of my viewers has coined this thing the beast, because I did have a couple of teaser videos that came out just to show some turning action. And I've got this tool. It is kind of snug in here. I didn't give it much. I want it to be precise and not chatter or anything, so it actually has a mild press fit. I think I'll blow that groove out. So I CNC machined this structure and this lathe bit pocket on the Haas TM1 mill next to us over there. Okay. So I did actually turn one of these parts already and hit the numbers within half a thousandths on the ID. So having this huge bar is needed for minimizing the flexure. But even this bar flexed a little bit when we were, or when I was machining the inside diameter. And I actually had to change the tool out. Originally I had a 30 thousandths tip radius on this cutting point, because every lathe bit has some sort of tip radius on it, so it's not an infinitely sharp tip that just breaks off instantly. But the 30 thousandths tip radius was too much of a cut at one time, and I was not getting a good finish on the inside, and I was flexing this bar ever so slightly. So when I switched out to the 16 thousandths tip radius on this little bit right here, then I got a much better surface finish, because there was less load, less side load pushing this bar over and causing a ring and a chatter. There was still a little bit, but got a better finish. But I did notice that I had to reset my zero location on the x-axis because the tool flex was different, and it accounted for, like, I think it was 6 thousandths of an inch on diameter, or 3 thousandths of an inch on radius. So I basically had to reset the tool position for the final cut, because this bar flexed a little less. So anyway, all right, well, we are going to cut. So right now this position is the final position that cut the first cylinder, but I don't want to just blindly cut a second one and hope that the numbers match again, because I did just flip this tool around. So the flex of this bar will be a little different on this cut than the last cut, because now we got a sharper tip here, so less side load. So what I'm going to do, since we have a one of one cylinder here, and it took a bunch of people before me a bunch of work to get to where we're at, I don't want to risk scrapping this part by cutting the hole or the ID too big. So I'm going to back off by, I'm thinking like 15 thousandths to be safe. And then we're going to run the CNC program that will cut the inner profile of this cylinder. Okay, so to do that, we are in the DRO mode. So I'm turning the knobs to impart movement in the Z and the Y, or the X and the Z direction. So that's how I'm actually moving this stuff. So hence this lathe does work great as a manual mill, or a manual lathe, because you can just turn these knobs and you get the same effect. But we're going to do CNC. So like I mentioned, I'm going to offset our X-axis by 15 thousandths of an inch, turning these knobs. So one knob is for Z and one is for X. We're going to do a coarse motion so we can get there faster. Then I am going to come to the 0 location, like so, and these dimensions are all in diameter. So every number up here is twice what actually moves on the radius of your cut down on the part itself. And I'm going to back off by 15 thousandths. And then I will hit X absolute. You can also go into mode and setup and tool setup and edit, and then do these X modifiers and Z modifiers to offset your tool location. But I just keep it simple. Our tool path is this one right here. Yeah, so our 0 location is this yellow X. The red dotted line is rapid motion. And then all the blue lines are our cuts. And it will show you the cutter actually moving through these operations. So we can zoom in. So this is one of the valve seats. This is a landing inside of the bore of the cylinder, and the other one is over here off screen. But we can move around and see exactly what our cut's going to look like. And yeah, so we cut in rapid with the red dotted line, and then we start facing off or hogging off material, 40 thousandths per cut. And it'll do a few steps where it actually skips this landing and then keeps cutting that direction, because it can't cut this line without hopping up and over. So it actually just goes here and then cuts. And then the final, there's going to be 2 finish cuts. The first finish cut and then the final finish cut, which is these 2 lines that follow the profile. And that is going to be our cut operation. All right, so we'll go to digital readout. And I believe we are set. So this cut does take a while because it's 250 RPM and like 1 inch per minute, so that we don't ring too much on our super boring bar. But what I'm going to do now is maybe we'll do tracking, which is a way to preview your program. So we're going to go to mode and then run. I'm going to hit the start button and we'll hit go, and then the boring bar will move to its home position, which is that sound you heard. And then I'll hit the tracking button, which allows me to walk through the program by turning the hand wheels instead of just hitting go and doing a Hail Mary and hope for the best. We can actually run through the program, and we do need the spindle on, so we'll hit forward on the spindle, and then we can do show. Oh, here's the program, by the way. It's a little cryptic, but it's conversational programming, but we're gonna do show path. And now I'm gonna turn this handle, any of these handles, and we are actually running the program, and as soon as I let go of the handle, the path stops moving. And then I can see what's happening up here as well, and it gives me the location, spindle RPM, and feed rate. Feed rate doesn't count because we're in the tracking mode. But I can come in real nice and gentle. And it looks like we're just going to cut air for this first pass. And the bar is not moving, but as soon as I start turning the hand wheel again, we are actually running the program. and I can speed it up if I want, because we're just cutting nothing right now. And if I don't like something, then I can stop and I can reverse. I can turn the wheel in backwards and back all the way out of the program if I wanted to, back to the home position. So let's go forward again. And you can see how it kind of got into the cut, like right there, even though we're backed off. I define the stock to cut as a little bit thicker than what we're actually cutting, so I could do an air pass to make sure that I'm not just gouging into metal and flinging this part across the room. Some things to consider is the coolant gets real jammed up here at the end. And I'm looking through the gap on the backside, this gap, to see the tool poke out through the jaws of the 3-jaw chuck. And I'm just getting a lot of visual confirmations that things are looking good. So yeah, this boring bar is as big as it is because it needs to reach all the way through this cylinder. All right, I see the tool poking out. But yeah, I see the tool tip right there actually. And I'll continue the program, and it's now advancing back out for the next cut. And you can see that with this little pink dot right there. That's telling you where the tool tip is right now. If I could keep it focused. All right, so I'm still turning the hand wheel counterclockwise, which is the cut direction. And you can see our bar is backing out and getting ready to take the next cut, which we're probably actually gonna start cutting cast iron on this pass. Yeah, I can hear it. And then we can adjust view. We can zoom in. I'm just skimming the leading edge of our part right now, but you can see the little pink dot right there. And I will start cutting, and you'll see that pink dot moving forward. I got it right there. Now this is all just rough machining right now. And I can back out again. And we can take a look at our chip, which looks good. I might have to switch to a telephoto lens. And so we can do tracking through the whole thing, or I can abort the program and then start the actual CNC program where I don't have to keep spinning the hand wheels, because I'm pretty comfortable with where we're at right now. So I'm gonna back out or just stop the program and go back to DRO. And then digital readout means I can move the tool out of here. And yeah, so that's what our chip looks like. Let me get the cell phone. All right, there's our lathe bit. And some of the chips back there. You can see how when I backed out on the cut, there's still a record groove, and that's mostly due to the inherent flex of the boring bar. Even though this thing is kind of substantial, it still flexes. And but that looks like pretty good chip. That's typical for cast iron. Sometimes you just get black sand, but here we actually have a little bit of a chip formation. Cast, I don't think ever gets stringy, but I could be wrong about that. Actually, I think it just turns into sand. But that's what we got. Yeah, so that's a 16 thousandths tip. The 30 thousandths tip was too much force on the bar. So we'll turn on the coolant. It's kind of nasty coolant. This lathe gets the hand-me-down coolant from all of the mills. But you can see how we're spraying right on our lathe tip here, and that should flush the chips out the front end of the cylinder for the most part, but we'll still get some stuff coming out the back. All right, so I'm going to go to mode, run, start, press go when ready. And then we move to our tool load position, or our start position. We'll turn the spindle on. And then press go for CNC run. And I'm going to override some things, like the spindle. We found out, I talked with Keith Rucker and found out what his feeds and speeds were, and he ran 250 RPM just like we are. You see the progress of our little pink dot if we can refocus. It's cruising along, this guy right there. And it kind of tells you how your progress is going. Now when you're running the CNC and the preview only shows a few passes ahead, it doesn't show everything. And then as you progress in the program, more and more of the preview blue lines for your next cuts will start to appear. You're gonna hear a chip getting in the wheel bearings of the steady rest every now and then, but I can't get the wheels farther away from the dumping edge of this cylinder because I ran out of room on the actual second rail on the lathe itself. So we're right at the point where we may not even need the steady rest. All right, this is the final finish. I'm wondering if I should cheat and stop it to measure it. Maybe I will. But I'd hate to cut this a few thousandths too big and ruin like a month of work from a bunch of different people. So 2.857, and that dimension, it should be 2.875. So we've got like 20 thousandths clearance, and this is our safe finish cut with an intended 15 thousandths. So it looks like I'm actually 5 thousandths over. So that's good. So I will continue the program. It's just paused right now. So we'll turn the spindle back on. And I can also check the finish, which looks pretty good, like the actual surface finish. And now we'll turn on our coolant. And I will hit feed go. And that gives me a nice warm fuzzy that I'm not ruining this part right now. Even though I got more chips in my ways. That sound is like a maybe 1,000th chip getting caught in the wheel between the cylinder and the wheels. The deeper we go, the less that's a problem because the chips go out the front end of the cylinder. So after this cut, I'm gonna measure the diameter that we've got, and then I'm gonna offset the tool and then basically do another finish cut. And what I'm doing is I'm recording the tool flex, the sharpness of the lathe bit, and the feeds and speeds to hit our actual ID. Because this tool is flexing right now. And it's a solid, or it's a continual deflection because we're not changing our feeds and speeds, and the lathe bit isn't dulling out too much within this final cut. So it's definitely a fluid operation. It's not just a set and forget when you need to hit like within 1,000th or less with such a long boring bar. Almost done. You can hear that ring. Now we're pulling out of the cut, right up next to the chuck. And then we'll back out. I've got the speed set at like a smaller amount. Here we go, we're done. You can see our little pile of chips on our tool there. All right, so we'll get out of the program mode, get back into DRO. We'll back out our boring bar, even though I was too lazy to take the tailstock off. So this is all the working distance I have on the back of the boring bar. And I didn't want to cut off this rough, hot rolled part either. So anyway, so we'll back our X off so I can get a telescoping gauge in here and measure our ID. Now, keep in mind I intentionally back this tool off 15 thousandths. And that's so I don't scrap Keith's part by not understanding the spring dynamics of this basically very rigid spring that we have, which is our boring bar, and the exact tip dynamics and the forces from this 16 thousandths lathe tip radius and the feeds and speeds. Now I did start the feeds and speeds a little low. I realized that my override was slow, and when you go into a finish cut, you can update the RPM and everything. So I'm going to go in and measure a little deeper. I'll probably actually measure the target landing, which is the only important thing, which I don't know if you can see with this lighting in there. But I'm going to get the telescoping gauge in and as square as I can get it. And then I will gently release, and you hear how it snaps in place. And then I will tighten it. I'm using the boring bar as kind of a parallelism guide. All right, and then you can roll the T-part out, and then this is the inside diameter. So let me get some calipers and we'll measure this. I'll probably do a better measurement off camera by placing the calipers on a table and getting my spacing just right, but this is mostly just for demonstrative purposes. But you want to measure perpendicular and everything and kind of in the middle of the... Okay, so we got 2.735. That's good. It's smaller than 2.750. So that difference I will offset in the tool, And then I'll run basically the same program. I'll probably abbreviate or get rid of the rough cut part. But the key is that we take off basically this close to the same amount of material that we just took off, so that the spring deflection and everything matches this cut, so that we can try to hit our target yeah, so that would be 14 thousandths. So I backed off the tool 15 thousandths, and we wound up measuring a 14 thousandths difference, 2.736 minus 2.750. So that's cool. All right, well, I did the second finish, and measuring with a telescoping gauge on the lathe, looks like I hit the number right on, 2.7500 inches. So let's get this thing off of here. To do that, we'll loosen the nuts on our bearing pedestals here, or whatever they're called, arms, to back them off of our finished part, or for, well, today's finished part. Ooh, I may have overdone it on that one. There we go. Open up our steady rest. One thing with track is this knob up here is about 10 thousandths too tall to go past the top of the carriage of the lathe. Okay, we can actually use the steady rest to support our stock as we loosen the chuck here. And I've got 2 jaws on the bottom. And we are done for today. So there's our ID. We'll take some measurements on the bench and get some closer pictures. But it looks good. All right, so we got our telescoping gauge here. And again, these are spring-loaded, or like telescopes. They come out. What I discovered I like to do is I actually pinch them shut by turning this handle at the bottom. There's 2 knurled things, and when you turn this, you release a wedge at the top, which causes these to snap out. But you don't want to like drag these, like push them in and then drag on your barrel. So I preset them to be smaller. Then I drop the tool into the cylinder, and I actually hold it up against the wall of the cylinder that's, you know, less than 1 diameter. And that way it won't spring and snap against the your part, and maybe even damage your telescoping gauge. So with me snugging up against the wall, the inside side wall of the cylinder, I'm going to release the wedge and then let it naturally drift to the center. And then I'll let it kind of settle in. I'm making sure the handle is still vertical. I'm going to grab the knurled fixed section of the handle, and I'm on the area I want to measure, and then I'll turn the second knurled knob, and that's basically wedging those telescoping anvils in place. And then that is our inside diameter. You don't want to whack this thing at all, because both of these anvils are spring-loaded and a wedge is holding them in place. So if you ring it by hitting it on metal or tap it with your caliper like prongs, then it's going to grow a little bit. Every time you get a little vibration through there, the wedge will release, you know, in a microsecond enough just for you to add a few more thousandths. So be very careful with this at this point. 2.750, but if I roll to make sure I'm not wedging the tool in there, 2.51, I can get it back to 2.7505. So I think it's 2.751, so I may be 1/1000ths oversized. But there I can move it in and out freely. So let's see if I can snug up on this jaw a little more. 2.750. Let me roll. So I'm rolling on the little round faces to clear the part out. So 2.7505 seems to be the dimension. So I'm a 1/2 thousandths big on diameter. And then this guy is the one I turned yesterday, so we can do the same measurement with this one. And I'm starting to prep these to go on the 5-axis. So I've got this 4-jaw chuck, which don't ask me why I didn't put it on the lathe. But this one is actually going to bolt onto the 5-axis CNC, the Haas CNC. But I want to double check this dimension from the other cylinder as well. Not to show off anything, but I already know it's the same number. But maybe it isn't now, I don't know. The cast iron did relax, I guess, overnight. You can also get the T slot to be in the middle, you know, of the two telescoping anvils, or probes, or whatever you want to call it. All right, I'm going to tighten that pretty good. We roll the tool out. It's hard to hold on to. Maybe just sitting on the table is good enough. See, that's too tight. I'm not on the apex of the dome of the telescoping gauge. Huh. All right. Interesting. I got 2.7505 on this cylinder yesterday, but today, with my coffee jitters, I'm getting 27500. Yeah, it looks like the cast iron cylinder relaxed overnight. Actually, having 1/2 thousandths undersize on the ID would be good for Keith, because he may want to hone these surfaces even more, but they look pretty good. I don't think they need any extra polishing or anything. Looks pretty good. Probably doesn't need any polishing. Let me switch to the cell phone. Okay, so here is the finish on our boring surface. So that landing there is, you know, like the 2.75 ID dimension that we're concerned about. That's where the actual seal of the spindle for the valve sits, and then there's another one further down. Let's see if I can drop the phone down in there and see it. So that's the second landing down there. So I don't think too much polishing is needed. I think I Brilloed this one, and then this one came right off of the lathe just now. So if I hit that with Brillo, it'll clean up a little more. Well, it looks like there's a little occlusion in the casting there. Huh. But you can see a little bit of the recorded ring from the bar, especially on that faceted surface. But all in all, I think we are good. So we hit the numbers. This one that sat overnight, 2.700 inches. And this one that we just machined is 2.705 inches. So 5/10 over. But if it behaves like this one did, then tomorrow it'll probably hit the 2.700 inches. Or I'm sorry, 2.7500 inches as well. Or 2 3/4 inch on the button. I did just wash it like 4 minutes ago, and I'm seeing some surface rust starting, those little red dots. So I'm going to hit this with WD-40 and let it sit overnight. All right, well, I think that's a wrap for this episode. Next week we will, or the next episode, and maybe sooner than a week from now, we are going to use the Haas 5-axis to machine all the portholes in the sides of our brand new valve sleeves here. So thank you for watching Dragonfly Engineering. Please like and subscribe, and if you want to hit me up on Patreon, there's information at the end of the episode here, and I'll see you guys soon. Thanks for watching. Bye.